Hey, what is up, guys? Welcome to the Organic Chemistry Revision Crash Course for the following topics: alkanes, alkenes, arenes, and halogenoalkanes. So the main thing I'll be going through with you guys is the chemical properties of these organic compounds. And without further ado, let's begin. So the first thing for alkanes that I want to talk about is that what is the general reactivity of alkanes? So to find out that, most of these organic chemistry concepts is usually based on visualization. So I would like you to visualize the concept so that you are able to write out the answer when you encounter such exam questions. So for alkanes, you know that, take for instance, ethane, which is C2H6. They contain CC and CH bonds. So what do you notice about CC and CH bonds is that they are very, very strong based on the data booklet. So on the data booklet, you can see that the bond energy are generally quite high, which is 350 kilojoule per mole as well as 410 kilojoules per mole. So these require high amount of energy to break the strong covalent bonds. Okay? Another thing you notice is that they are generally non-polar as well. So how do I know it's non-polar? The fact that the carbon of CC bonds are of the same electronegativity, as well as the fact that carbon and hydrogen of CH bond are around of the similar electronegativity. So I know some of you can argue that hydrogen is actually less electronegative than carbon, but I wouldn't say the electronegativity difference varies that much. So that is why we say that these bonds are non-polar, and there is not, I would say that there's a lack of nucleophilic and electrophilic sites. And we can say that confidently that because we can't really draw out a partial positive and partial negative charge. So because of the lack of a partial positive and partial negative charge, or I would say a strong partial positive and strong partial negative charge, that's why you are not able to attract and react with nucleophiles, electrophiles, acids, bases. So that is why alkanes are generally unreactive. And that is also why we can't really heterolytically break a CH or CC bond, because they are very strong and they are non-polar. So this kind of heterolytic fission where two of the bonding electron of CH bonds is taken by one of the atom, this is a no-go. So this is not allowed. So because we can't really go through heterolytic fission, so we always want alkane to undergo homolytic fission, which is way better because then I'll be able to form highly reactive radicals. So instead of drawing a two-headed arrow, I will draw a single-headed arrow where one of them absorbs the whereby one of the bonding electron of CH bond is taken by each of the atom. Okay, so that will help you form highly reactive H radicals as well as this radical over here. And these are very highly reactive. So some of the Maslow reactions in the A levels for alkanes are just combustion and free radical substitution. So in a sense, you do not need to worry too much about the reaction for alkanes. So in general, we have complete combustion and incomplete combustion. So in incomplete combustion, we always use excess oxygen gas, heat at high temperature and pressure. So You do not have to remember these reagents and conditions diligently. Okay? So all you need to know for this is that all you need to know for complete combustion is how to balance the chemical equation. And this is generally how you balance the chemical equation. CXHY plus X plus Y over 4 O2 gives you XCO2 plus Y over 2 H2O. And if you want to know how to balance, the only product that contains carbon is carbon dioxide. So I'll balance carbon first. That's why I put X beside carbon dioxide. Then the only product that contains hydrogen is water molecule. So I decide to balance the water molecule next and give it a Y over 2 so that I balance out Y hydrogen atoms on both sides. Then the last one is oxygen. So for oxygen, I have 2x and y over 2. So 2x plus y over 2. And because oxygen have two oxygen atoms, so I would end up dividing this whole thing by 2 to give this. Alright, so this is how you do your balancing. Okay, I'll erase all of this. And then observation, you will see that it burns with a non-luminous flame. So it's a blue flame and carbon dioxide is produced. So you can see that the single bond of the hydrocarbon is being oxidized to C double bond O of carbon dioxide. And that is why it is a complete combustion. So for incomplete combustion, to know is incomplete combustion is limiting oxygen and you hit that high temperature and pressure. But the chemical equation, as long you give a valid answer where you balance out all your hydrogen, carbons, and oxygen, it will be given. And observation is usually that black soot form and it burns with a luminous orange flame. And the reason why black soot form is because not all the carbon in this C6H14 hydrocarbon is being oxidized to our desired carbon dioxide. So instead of oxidizing the C and CH bonds into carbon dioxide, I'll only be able to oxidize it to carbon monoxide. So to know, so as you can see that if I because we know that oxidation is a sorry, we know that combustion is an oxidation process. So in this case, if you want to draw out the if you want to know the oxidation state, you can see that this carbon is a -3, this carbon is a -2, and then you so on until we reach the sixth carbon. So usually for this one, C6H14, my carbon will have a -2 or -3 oxidation state. Whereas carbon monoxide, it will be a +2. So you can see in carbon is 0. Whereas for complete combustion, I will have my carbon being oxidized from C4H10, where my oxidation state is -2 and -3, to the highest oxidation state of +4. So that's why that is essentially the difference between complete combustion and incomplete combustion is comparing the change in oxidation state between both reactions. The change on oxidation state of carbon. Okay? And for the next reaction we'll look at is free radical substitution. So in general, halogen is being used as a reagent, and this is because most halogen bonds are generally weak and easy to break. So they have generally a low bond energy. So fun fact, actually, if you can think about other weak bonds, OO bond is also weak. So sometimes hydrogen peroxide also undergo this free radical substitution. And most of these reagent conditions for halogens, I want it to be in gaseous state because, as I said, alkanes are generally unreactive. So because of the strong C and CH bonds, so that's why I want my reactants to move at very high kinetic energy so that they have a higher frequency of effective collisions and essentially higher rate of reaction. Alright? And I usually use UV light for this to this UV light is very important because for free radical substitution, I want to generate free radicals. So if I want to generate free radicals, right, you need to have this thing called a radical initiator. So if you want to have a radical initiator, one common radical initiator is actually UV light. And this UV light, which I'm gonna show you later, there's a reason why some exam questions they test on this is that a brief exposure of UV light is needed, and it's because you want to initiate the homolytic fission of the halogen bond to generate these halogen radicals, which are highly reactive. And why they are highly reactive is because they are they have single unpaired electron. And when you have a single unpaired electron, you would want to pair up with another radical with this single unpaired electron so that both your radicals will be able to adopt the stable octet structure. And why a brief exposure only? The second bullet point provides the reason why only a brief exposure is needed. It's because you will produce these radicals, and these radicals will initiate chain reactions of the propagation step to produce more radicals to sustain the reaction. So later on, I'll show you that these chain reactions of propagation step, the propagation step will actually show the reaction between a radical and a neutral molecule to form another radical and a neutral molecule. And this process keeps repeating. As long as I have radicals, which I say is very reactive, I'll be able to pair these radicals. I'll pair I'll be able to use the unpaired electron for these radicals and pair up with another radical or molecule. So that is why UV light is can be used as a radical initiator. And because of this second reason right here is also the reason why the ozone layer is actually depleting. Because radicals that are forming from chlorofluoroalkanes reacting with the ozone layer, every time it would be able to produce even more chlorine radicals to react with the ozone layer. Okay? So to go back to this, we always also have to mention whether is it in excess or limiting, because in free radical substitutions it's generally a very uncontrollable reaction. So most of the molecule they have no fillings. So they generally no fillings what. So any hydrogen of this molecule right here, any hydrogen, I can actually react it with uh yeah, any of these hydrogen right here, I can actually replace it with a chlorine atom. So this part they say draw the major product form, and to be able to identify what is a major product form from this reactant right here, I would want to ensure that I want to ensure the most stable radical is being produced so as to form the major product. Okay? So I would before I go on and talk about the what is the ratio of products being formed, I think I would want to show you how the mechanism looks like. So this is how the mechanism generally looks like. First off, specify what type of mechanism it is. And then we would have three stages. So three stages is initiation, propagation, and termination. So one way to remember is that initiation starts with a I, propagation starts with a P, and have another P. So it's actually double P. And the last one is termination. So you can see it's actually an acronym for IPPT. Okay, so IPPT. Okay, so for initiation, I would want to, if I want to initiate the reaction, from the name of the mechanism, substitution is an atom substituted by another atom. So a hydrogen of my alkane molecule being substituted by a chlorine atom. And free radicals must be involved. So initiation is in the sense that I would want to generate my free radicals. And to do that, I would use UV light to initiate the homolytic fission of Cl-Cl bond to form highly reactive chlorine radicals. Okay, so that's one, the very first initiation step. Second is propagation. So the idea for propagation you need to know is that a radical react with a neutral molecule to form a radical and a neutral molecule. So that on both sides I must see a radical. Alright, so in this case, chlorine radical react with this neutral molecule right here. So the bonding electron of the CH bond, one of it will go and pair up with the chlorine radical. And then the other one will go and pair up with, the other one will actually be taken by carbon. Alright, so I will form HCl plus this tertiary radical right here. Okay, so in this case, just to be clear, I would want to form, at the end of the day, for this free radical mechanism, I will want to form, I want to form, uh, I want to convert this and form 2-methyl, sorry, 2-chloro-2-methyl propane. So just a clarification if in case you guys don't know. So the tertiary radical, what I do next is, remember, a radical plus a neutral molecule. Since Cl-Cl bond is weak, I can let it undergo homolytic fission. And I want to pair the unpaired electron of the tertiary radical, pair them up with one of the bonding electron of the Cl-Cl bond. And then one of the Cl atoms takes one of the bonding electron of the Cl-Cl bond to form our desired product. Okay, so as you can see right here, what do you notice? The chlorine radical is being consumed at the first step and being regenerated at the second step. So what idea is this? This is catalysis, okay? And not just catalysis. We know that all these radicals are generally in gaseous state. So in gaseous state, that means that it is a homolytic catalysis because my chlorine radicals are in the same phase. One thing before I go into termination is that a common mistake by most students is that they would homolytically break the CH bond, and instead of forming the tertiary radical, I would form the hydrogen radical instead and form the final product in the very first step. However, for this step, it is not feasible because this hydrogen radical is very unstable. Okay, it is very unstable. So another thing is that if you calculate the endothermic change of the enthalpy change of reaction, okay, the enthalpy change of the reaction, you use bond break of CH bond minus bond formed, the bond energy from the bonds being formed. So that is your HCl. So that's your CCl. I will get a plus 70. So an endothermic reaction means that it is a very energetically unfavorable reaction. So this is a no-go. Okay, this is wrong. I'll move on with termination. Termination, the idea of termination is that I want to terminate my reaction. So I would want my radicals to stop further reacting with other molecules. And my product of the termination reaction should not contain a radical. So at the end of the day, I will want my radicals to react with each other to form a neutral molecule. So we're gonna take all the radicals that are being formed in the reaction and homolytically fuse with one another so that I form a neutral molecule. And then this goes the same for the tertiary radical. Pair them up with a Cl radical. And then lastly, two tertiary radical pairing up. Okay, so this is the mechanism for the free radical substitution. And like what I said in earlier, uh, you have to specify whether it is limiting or in excess. So if it's in excess, chlorine, what is gonna happen is that the product being formed. So in this case, if I give you Cl2 plus 2-methylpropane, so if this is in excess, this is limiting, this thing will be gone. The 2-methylpropane will be gone. So we will not have 2-methylpropane. The product, we will have the product and the HCl product. So in our final mixture, imagine our final mixture will only contain this molecule and this two molecules. So you can imagine that this 2 chloro 2 methylpropane, because it still have CH bonds. If they still have CH bonds, I can still further react this molecule with chlorine gas. Okay, so you can imagine this thing will undergo homolytic fission again, CCl radical, and my propagation step, what will happen is one of the CH bonds will undergo homolytic fission with the Cl radical, and I will form these two products and continue react it further, and I get a dichloro product. Okay, so this is why when you have excess chlorine, multi multi-substituted products can be formed. Whereas if you use limiting, right, this means that this one will be gone. And in my reaction mixture, I have these two, these, I will have this and this one left. So that is why, and you can see right here, there's no chlorine gas anymore. So it cannot, I use this 2 chloro 2 methyl propane cannot further react with more chlorine. My bad. Yeah. So that is why. Okay, let's move on. And normally for observation, we always link it back to the equation. So our greenish yellow chlorine gas will fade, and we have steamy white fumes of HCl gas being produced. Okay? And now I will move on to the statistical. Actually, no, I'll move on to say that. Remember I told you about the reagents, halogen, right? Not all halogens can be used because iodo-alkenes cannot be more difficult to produce, and that is because if we calculate the enthalpy change of reaction, generally these are endothermic and energetically unfavorable. Okay, so it's also because the I bond is generally quite weak. Yeah. So stability of intermediates. This one, that generally the relative ratio is being tested in exams compared to the statistical ratio, but I'll go through both. So in essence, uh, if you think about this molecule right here, the 2-methylpropane, you would expect that what kind of product to be formed. So you expect either this or this product to be formed, correct? And the expected ratio, you expect that this molecule right here would form in greater quantity. If you use the concept of the number of substitutable hydrogen in 2-methylpropane. Because you see right here in 2-methylpropane, right, there are clearly two different chemical environments of hydrogen, which is the primary and the tertiary. So there are 9 primary hydrogen, Ha, and there's 1 tertiary hydrogen, Hb. So in comparison, you expect that the ratio will be 1:9 because I can substitute any one of the 9 Ha the to form this product right here. Whereas I can substitute any of the whereas I can just substitute 1 Hb only to form this product right here. However, in actual fact, this statistic ratio is not uh I'll say the experimental actual relative ratio is not 1:9. So it's because of the electronic factor. So in this case, I will expect product more of product A being formed compared to product B. Okay? So that is because to form product A, I will form a tertiary radical intermediate. So a tertiary radical intermediate looks like this. And to form B, I would form a primary radical intermediate. So what's the difference between tertiary and primary? Tertiary, you have 3 electron donating alkyl groups being bonded to the carbon containing the radical, whereas for primary, there's only 1 electron donating alkyl group. So in this case, the electron deficient, in this case, right, the electron density of the electron deficient radical of the tertiary radical, right, would increase to a greater extent due to more electron donating alkyl groups. And that is why a tertiary radical is more stable than this, and thus a higher rate of reaction to form A. And that is why the proportion of A being formed is more than the proportion of B being formed. Okay, so this is generally the answer format that you need to remember. Okay? And another thing is that there's this thing called the inductive effect versus resonance effect. So I'll talk about inductive effect first, and then um, resonance effect when we reach there, then I'll talk about it. So inductive effect is the donation of or withdrawal of electron density via the sigma bonds. And this is usually originated due to the difference in electronegativity between two atoms, also known as polar bonds. So for let's say if I give this molecule for instance, so this is a carbocation. Okay, maybe not carbocation. If I say this is a electron deficient carbon radical. Okay, you can see that generally I have the polarity is pointing, the net dipole moment will actually point in this direction. So in a sense, this carbon right here will accumulate more electron density compared to the hydrogen of the methyl group. And that is why we call these methyl groups or alkyl groups as electron reservoirs to donate the electron density to the electron deficient carbon radical. Another way to look at the inductive effect is to use the idea of hyperconjugation. So hyperconjugation is that you know your radical, right? Is this unhybridized p orbital, okay? And all these other CC and CH bonds are actually represented by sp3 hybrid orbitals. So sp2, actually what am I talking about? It's sp2. sp2 hybrid orbitals. Okay, it's a trigonoplanar intermediate. That's why you have this. You have three sp2 hybrid orbitals and one unhybridized p orbital. So in this case, this sp3 hybrid orbital of CH bond, it will actually sort of sideways overlap with the p orbital, and the bonding pair of the bond electrons for this CH will delocalize or quote unquote delocalize into the p orbital of the radical carbon. And that is how you stabilize the carbon radical. Okay? So this is called the hyperconjugation effect. You do not need to know all this, but it's just for your understanding. Okay, so now let's move on to... Okay, this is an interesting question. So you can see that in this chemical equation, my double bond is converted to a single CC bond. So this suggests that an electrophilic addition has occurred to because my uh nucleophilic pi electron cloud it attacks the electrophilic bromine gas. Okay, so the pi electron cloud actually polarizes the bromine gas molecule to ensure that there is partial positive charge and partial negative charge of the bromine, and ends up attacking the partial positive charge of the partially positive bromine atom. Okay? And it will cause electrophilic addition. Then you can see that all the hydrogen are also being substituted by bromine. This suggests free radical substitution because your CH bonds are too strong and too nonpolar to even undergo heterolytic fission. Okay, so since all of the hydrogen is being substituted, so that's why I say excess bromine gas or bromine liquid, and in tetrachloro methane solvent, so as to prevent the possibility of side products being formed. And the fact that generally these these organic compounds, right, they are generally soluble in these non-polar organic solvents. Okay, UV light is used in room temperature, so it's really a mixture between the RNC we propose right here is a mixture between the RNC for FRS and EA. Okay, observations, you just take reference with the chemical equation. Environmental consequences of harmful gases. This, I'll leave it to read by yourself mostly. Most of these are actually from the reaction kinetic notes. But one key idea that I want you guys to take away is that um, the harmful gases are being converted to the harmless gases. So carbon monoxide, yeah, we oxidize in air to form carbon dioxide. The nitrogen monoxide gas will be converted to nitrogen gas. Nitrogen monoxide, carbon monoxide converted to nitrogen and carbon dioxide. Nitrogen monoxide, unburned hydrocarbon, they will be converted to nitrogen gas. And then the unburned hydrocarbon of C8H18, they will be oxidized to CO2 and uh water. Okay, so now, and you can see the unburned hydrocarbon right here oxidized to carbon dioxide and water. Okay, then the greenhouse gases. Okay, this one can read by yourself. Because honestly, most of this stuff, right, the learning objective not commonly tested in exam, but it's still a learning objective, so you guys have to still read up on it. Petroleum, there's also this part on petroleum and recycling. So what is the main idea is that petroleum is actually you just listen out the main idea, but the rest you can read by yourself. So the main idea is that petroleum is a finite resource. So if you know this thing, for example, you know how organic compounds have many useful applications, so such as plastics, they contain polymers. So plastics are actually originated from petroleum, if you think about it. So the fractional distillation of petroleum will give you ethane, okay? And this ethane will go through free radical addition to form polyethylene, okay? So afterwards, then you know that this polyethylene is actually your plastics. And we all know that plastics are non-biodegradable. So you know that plastics are non-biodegradable in nature, so they can't really decompose. And it's very difficult to dispose plastics as well. Okay? So it's because if you want to dump plastics in landfill sites, it will take up a lot of valuable space. And then if you burn plastic, it will cause air pollution. So all this stuff about all these problems relating to plastics, and also the fact that we have many useful application for plastics, right? So in this sense, we should recycle, reuse, and reduce plastic. We should reduce plastic waste and reuse and recycle plastics as much as possible. This shows the importance of recycling. All right, and because plastics come from this finite resource of petroleum, it all the more justifies the need that we need to recycle plastics. Okay, so now let's move on to, okay, before I move on to alkenes, I will do a few practice questions regarding alkanes. So let's see how much time. Okay, so I will do this particular question on NYJC as well as TMJC paper. So the first question is that light of a longer wavelength is lower in energy than a light of a shorter wavelength. Outline the mechanism of the reaction between ethane and bromine to form 1,2-dibromoethane. So I will do it right here. 1,2-dibromoethane looks like this. So you have two bromine and two. Okay, so what's next is we want to convert ethane into this product and use a mechanism. So first up is free radical substitution, initiation. So bromine, take one bonding electron each, UV light, two bromine radicals, propagation. We know that it takes two steps to form a mono substituted product. So if I want to form a di-substituted product, I'll need four steps in total. Because I say two steps is all it takes to form mono substituted product. So in total, I'll need four steps. You understand that? So in this case, um, and bromine, I would react with ethane to form HBr and the ethene radical. And then this ethene radical, I'll react it with the bromine molecule. And this forms the mono substituted product. Alright, so this is two steps, then another two more steps to go. Okay, for last but not least, the termination step. So termination step, recall that I would want every single radical reacting with each other. So in total, there should be remember in total for mono substituted products, I will need three termination steps. In di substituted products, I'll need six, so times two. By the way, this is butane, by the way. Let's say this is actually butane. Uh, you can see that actually there's a lot of side products being formed from free radical substitution, and this is why most of the time for free radical substitution we do not use in synthesis question unless it's absolutely necessary. So okay, so this is the answer for the mechanism question. So in total I need one initiation step, four propagation steps, and six termination steps. So it's a very complicated. Um, it's more complicated than you think. So the second part is use your mechanism to explain why bromination of methane, or in this case, okay, sorry, it's not methane, it's actually ethane. Because I modified this question a bit. Bromination of ethane can be carried out with a light of a longer wavelength. So a longer wavelength means lower energy, right? So what's the difference between bromination and chlorination of ethane? So bromine is being used or chlorine is being used. So bromine, generally they have a longer bond length because of the larger atomic radius of bromine. Okay, so a weaker Br-Br bond will generally need a lower energy to break the weaker bond. Okay, because the Br-Br bond is longer and thus is weaker, and that is why less light energy is required to break the weaker bromine-bromine single covalent bond. Okay, so we're gonna write it out for you. Is that Br bond length is weaker than Cl bond length. Hence, less energy is required to break the bond for the initiation step of the mechanism. It's a one mark question, so I wouldn't say you need to write a lot. However, if um it's more marks, right? I would want you to explain why Br-Br bond length is weaker. So this means that you have to say that Br has a larger atomic radius or size of valence orbital than Cl, longer Br-Br bond length than Cl bond length. And then talk about the degree of effectiveness of orbital overlap for Br-Br bond is higher. And thus, Br-Br bond is weaker than your Cl-Cl bond length. And thus, less energy is required to break. Okay? For this question in particular is actually similar to what I have been going through, so I will not go through this. TMJC paper, I will not go through the homolytic fission definition, but I'll in particular go through the mechanism for this question. So the mechanism is a novel mechanism, in fact. So to do this type of novel mechanism, read the question carefully and follow the steps. Usually these novel mechanism question, they will give you step-by-step instruction on how you do the mechanism. So let's do this together, alright? So hydroxy radicals are generated from hydrogen peroxide through photocatalysis via homolytic fission. So homolytic fission means that each of the oxygen of the OH will take one of the bonding electron of the OO bond. Okay? Photocatalysis means that light is being used to catalyze the reaction. So the OO bond would absorb the light energy to initiate the homolytic fission of the OO bond of hydrogen peroxide. Okay? And fun fact, right? Um, your OO bond is actually quite a weak bond. So that is why they generally go through homolytic fission to form these highly reactive hydroxy radicals. So the second step, they say hydroxy radical abstract a hydrogen from methanoic acid to form an intermediate and water. Third step, hydroxy radical abstract a hydrogen from the intermediate forms carbon dioxide gas and water. So let's apply all these steps and do this question, alright? So you need to show the structural formula of the intermediates, the movement of unpaired electron using the curly arrows, and indicate any unpaired electron using a dot. So the first step we see is that they say the first step is homolytic fission and hydroxy radicals are being generated. So I need to ensure two hydroxy radicals are being generated, and I use a single headed arrow to point to the oxygen, such that each oxygen takes in one of the bonding electron of OO bond. And this is what you call homolytic fission. Second step, hydroxy radical abstracts a hydrogen from methanoic acid to form an intermediate and water. So they already give you the thing. Hydroxy radical, this is hydroxy radical. It abstracts a hydrogen from methanoic acid. And this forms water. Okay, you can see where the atoms are going around. Then intermediate, we see that this uh single-headed arrow going towards oxygen. So that is why my intermediate I will draw will be this, where the oxygen takes in one of the bonding electron of OH bond. Okay, now next step, the hydroxy radical abstracts a hydrogen from the intermediate and forms carbon dioxide and water. So this hydroxy radical will abstract this hydrogen of the intermediate and it will form water. Okay, so see where the atoms are going and then let the arrows do the work. Okay, so this will form water. And then now how will you form carbon dioxide? So to form carbon dioxide, I need to ensure another CO single bond is being formed. So to do that, one of the bonding electron of CH bond will pair up with the unpaired electron of the oxygen. So this is what will happen. Okay, and this will result in the formation of CO double bond. And there you have it. So this is the chapter for alkanes. I would take a break because the video is getting a bit long. And the next part will address alkenes. Okay?